Dear students, I am Ramesh, chemistry faculty from Vidya Mandir Metric Higher Secondary School, Uttangarai. Let us discuss application of VBT in coordination compounds. Here, application of valence bond theory. We are taking an example, nickel tetracarbonate. Nickel tetracarbonate. And for this, first we may write that the electronic configuration of nickel. So, the electronic configuration of nickel is 3D8 and 4s2. So, it is nickel. And in this complex, nickel as the oxidation state of nickel is identified. Now, here CO is a neutral ligand and the oxidation state of nickel, there is no loss of electron. So, oxidation state of nickel is 0. So, here in this complex, electronic configuration of nickel is 3D8 and 4s2. Now, we may take that the outer orbital of central metal atom. Outer orbital of central metal atom. Outer orbital we are take 3D8. So, here it is d orbital will be splitted into 5, 1, 2, 3, 4, 5 and we may take the electron fill up 1, 2, 3, 4, 5, 6, 7, 8. First singlet and after that doublet. And here it is 4s2. So here it is 3d8 and 4s2. So 2 electron. And after that here it is 4p orbital. So 4p is 0. So we may write the outer electronic configuration. And we may take the next one here. The nature of ligand is noted. So here the nature of ligand. So we may take the nature of ligand. What is the ligand here? It is a CO. So here CO is a nature of ligand and it is considered as a strong field ligand or weak field ligand. So CO is a very strong field ligand. So it is a strong field ligand. So it is a strong field ligand. So why, if you are using a strong field ligand, what will happen? Here the pairing occurs. What is the pairing here? 4s orbital electron is paired with 3d8. So strong field ligand is present in a complex. Pairing occurs. So it causes pairing. It causes pairing. So we may take the outer orbital in presence of ligand. In presence of ligand. So the outer orbital in presence of ligand, we are writing here it is pairing occur. So here that is 1, 2, 3, 4, 5 and here 4s orbital. So here it will be vacant and it will be paired. So totally 10 electrons. So it is paired. So first singlet and after that doublet. And 4s is vacant and that 4p is vacant. So here pairing causes due to CO is a strong field ligand. Now we may take that the hybridization. So hybridization. And for hybridization we may take that the coordination number of a complex. So what is the coordination number? Here the coordination number is 4. So we may take the coordination number. So coordination number is 4. And coordination number is 4. So the hybridization, it required 4 vacant orbital. So these 4 vacant orbital undergo hybridization. So what is the hybridization here? It is S. And here p orbital. So p1 and p2 and p3. So the hybridization, it is px, py and that pz. So the hybridization is sp3 hybridization. sp3 hybridization. So here this sp3 hybridized orbital of a central metal atom is filled with the ligand electron. So lone pair of ligand is filled up with this sp3 hybridized orbital. So we are taking that the next compound here, that is so outer orbital or hybridized orbital. Hybridized orbital. So hybridized orbital of central metal atom. So hybridized orbital of central metal atom, here the d orbital is filled up. So here 1, 2, 3, 4, 5. So first singlet and after that doublet. And here sp3 hybridized orbital, and it will be become equal energy. So that here 1, 2, 3, 4, then 1 s orbital and 3 p orbital, and it is filled up by that the lone pair electron of a ligand. So that it is sp3 hybridization. Now we may take that the magnetic character. Magnetic character. So magnetic character, here there is no unpaired electron. No unpaired electron. So that here n is equal to 0. So we are taking mu s is a spin only magnetic moment, and here it is root of n into n plus 2 Bohr magnetron. While substituting n equal to 0, so that it is 0. So the mu s is 0, then it is considered as diamagnetic character. Diamagnetic character. Now we may take the geometry. So we are taking the geometry of a complex, and geometry of a complex is identified by the hybridization. So what is the hybridization? It is sp3 hybridization. And if it is a sp3 hybridization, then it is tetrahedral in shape. Tetrahedral in shape. So it is the geometry tetrahedral. Now we may take the second example, that is NiCN 4 times 2 minus, that is tetracyanidonickelate 2 ion. Tetracyanidonickelate 2 ion. Now we may take that the electronic configuration of nickel. Electronic configuration of nickel, that is central metal atom. Then what is that? It is 3d8 4s2. And in this complex, what is the oxidation state of central metal atom? Now we may take the oxidation state. Here X is a nickel, and here that is a minus 4, X minus 4, which is equal to minus 2. So X which is equal to plus 2. So nickel is plus 2 oxidation state. Nickel is plus 2 oxidation state. So here the electronic configuration of nickel 2 plus ion, and here 2 electron is removed, so that here it is 3d8 and 4s0. Now we are taking the outer orbital of central metal atom. Outer orbital of central metal atom. Now, what is at the outer orbital? It is 3d8. So here 1, 2, 3, 4, 5, and first singlet, and after that doublet. So 5, 6, 7, 8. So 3d8. And here it is 4s0. So 3d8 and 4s0. And here it is 4p. So 4p0. So it is outer orbital of central metal atom. Now we may take the nature of a ligand. Nature of ligand. So what is the nature of the ligand? Is it is a strong field ligand or weak field ligand? We want to find out. And here Cn is a strong field ligand. Cn is a strong field ligand. So it is a strong field ligand. Now what happen when strong field ligand is present. So when strong field ligand is present, then here the causes pairing. It causes pairing. So here it causes pairing. So here the 2 electron will be present, then it will be paired up. So it will be paired up. So it will be causes pairing. So we may take that the next one, outer orbital in presence of ligand. In presence of ligands. So outer orbital in presence of ligand. So there is pairing. So we are taking that here 5 orbital and it will be paired up. It will be paired up. So totally 8 electron is there. Then it will be paired up. Now here it is 4s0 and 4p0. So it is 3d8 and 4s0 and 4p0. Now here we may take the hybridization. Hybridization. So listen, we are taking that the hybridization. Hybridization. So hybridization, we are taking that the coordination number. So here the coordination number. So coordination number is 4. And here hybridization, it is sp3. So here hybridization. So hybridization is here dsp2. So we are taking the hybridized orbital of a central metal atom. Hybridized orbital of central metal atom. So what is it? Here the 5 orbital, only 4 become paired up. So here 1, 2, 3, 4, 5, 6, 7, 8. So it is 3d8. And one of the d orbital undergo hybridization. So here it is d orbital and here 1 d orbital and 1 s orbital and 2 p orbital, 1 pz orbital is remaining. So it is 4 pz orbital. So here it is a d orbital and s orbital, px and that py. So the hybridization is dsp2. dsp2. Now that is the lone pair of electron is donated by the ligand is filled up in that hybridized orbital. Now we may take that it is dsp2 hybridization. So we are taking that the geometry. So the geometry of a complex is determined by hybridization. What is hybridization? It is dsp2. dsp2, so that it is a square planar complex. This is a square planar complex. And here magnetic moment. Magnetic moment here n is equal to 0. So mu s is equal to root of n into n plus 2 pm and it is become 0. So that the magnetic moment is diamagnetic character. Diamagnetic character. So it is a diamagnetic. Okay. So we may take the next one. It is limitation of VB theory. Limitation of VB theory. So the first limitation, it does not explain the color of a complex. So it does not explain the color of a complex. And the second limitation, and it will be considered only spin only magnetic moment and it cannot consider other component of magnetic moments. So it considered only spin only magnetic moment mu s and not considered other components. Not considered other components of magnetic moments. Other components of magnetic moments. Okay. And the third one, here it does not explain quantitatively why some complexes are inner and why some complexes are outer. So, not explain quantitatively why some complexes are inner and some complexes are outer. So inner and outer complexes. What is that inner complexes? DSP2 or D2SP3. If it is outer complexes, SP3D2. So these are the limitations of VB theory.